first question we're gonna ask this week is a question that's deceptively simple. What is energy? Pause the video and give it a good think. Energy can have a lot of different definitions depending on the context. And I know at 8:15 a.m., many of us wish that we had more of it. In this class though, we'll use Dr. Orna's energy and define it as anything that is capable of causing a change in motion. And this covers many forms of energy, including heat, light, nuclear energy, battery power, etc. But we said in the intro video that we were going to focus on light specifically. So what exactly is light? Light is a specific type of a broader range of energy called electromagnetic radiation, or EMR. This is a class of energy types that move through space as waves and generate an electric field along the way. But even though we can't see light propagating, doesn't mean that it isn't. Although we can't see the individual light waves, we can see what we can see because of light hitting our eyes after it bounces off of objects. In fact, light moves very quickly at a speed of 2.998 times 10 to the 8 meters per second. This number is so important that we give it its own symbol, lowercase c. But to understand and talk about the physical properties of light, we have to understand waves. So let's take a look at some of the property of waves. First of all, the height of the wave, as indicated by these arrows, is the amplitude. The tip top of the wave is the crest, while the bottom part is the trough. Crests and troughs are super important because they're the foundation for arguably the most important characteristic of waves. The distance between two crests or two troughs is known as the wavelength, which is a distance that is measured in meters. Now, the wave we have here is a snapshot of a wave. It's in 2 dimensions and doesn't appear to be moving. But in the reality, the wave is continuously propagating or moving forward. The measure of this property is called the frequency. Definition-wise, the frequency is the number of crests or troughs that pass through a same point in a second. The unit is 1/second, second to the -1, or per second. We also use the term hertz, or capital H lowercase z, to mean 1/second. The implication here is that it's the number of cycles that occur or peaks that pass per unit time, in this case, second. The frequency and the wavelength have an inverse relationship. If a wavelength is smaller, the peaks will be closer together, and therefore more peaks will be able to pass through one point in a second, like the wave on the top right of this diagram. If the peaks are further apart because the wave has a bigger wavelength, then the frequency will decrease because fewer peaks will be able to pass through a given point per second, like the waves on the bottom right of this figure. We have a chemical relationship between these two properties, and they are related to each other through the speed of light. The speed of light, c, 2.998 times 10 to the 8 meters per second, is equal to the frequency of a wave multiplied by the wave's wavelength. The unit wavelength, m, multiplied by the units of frequency, 1/s, give us meters per second, or a rate, or a speed, the speed of light. So as long as we know one quantity, the wavelength or the frequency, we can figure out the other, because their product is always equal.
Now let's practice manipulating this equation. WFAE is a public radio station in Charlotte with a frequency of 90.7 megahertz. Or what is the wavelength of the radio waves associated with this station if it has a frequency of 90.7 megahertz? Pause and give it a try. The first step is rearranging the equation to solve for the wavelength. What we know is that c is equal to 2.998 times 10 to the 8th meters per second. We know that the frequency is 90.7 megahertz. So we can arrange the equation to solve for lambda. We can divide c by the frequency to give us lambda. But first we have to make some changes. we're in megahertz and we have to convert to hertz. The multiplier m for mega means 1 times 10 to the 6th. So if we set up our conversion, we'll end up multiplying our value in megahertz by 1 times 10 to the 6th to get a frequency of 9.07 times 10 to the 7 hertz. Now, we plug this into our rearranged equation, and we get 2.998 times 10 to the 8 meters per second divided by 9.07 times 10 to the 7 per second. Seconds cancel, and we end up with a wavelength of approximately, 3.31 or approximately 3 meters. For reference, that's taller than most humans.
The wavelength is super important because it determines the properties of the wave. What do I mean by this? Well, remember when I said that light as we know it is only one type of electromagnetic radiation? There's a whole range of different types of electromagnetic radiation. And the identity and properties of the radiation are determined by its wavelength. An illustration here organizes the different types of waves by wavelength in your skeleton notes. On the left-hand side, we have waves with short wavelengths or high frequencies, gamma rays and X-rays. To the right, where we have waves with long wavelengths or small frequencies, like radio and TV waves. For the vast majority of the spectrum, we can see or feel the effects. E.g., we've seen images taken with X-rays, we listen to radio stations, and we heat up our food in a microwave. But the region where we can actually see light is really small, and it only takes up a tiny fraction of the spectrum. The visible portion only includes light with a wavelength of 400 to 700 nanometers in length. We can further subdivide these regions. Each color of the rainbow has a bandwidth or corresponding range of wavelengths that result in that color. From 400 to 430 nanometers, we have violet, 430 to 490 is blue, 490 to 560 is green, 560 to 590 is yellow, 590 to 610 is orange, and then 610 to 700 is red. You may notice that not every color has the same width. For instance, yellow and violet are relatively narrow. It turns out we can even subdivide these further. On different tables provided by different sources, you may even see extra colors like cyan or blue-green. But for this class, these are the ranges we're going to use. You'll also notice that immediately to the left of the visible region is the UV or ultraviolet region, coming from the close proximity to violet light and with a wavelength slightly shorter than the visible, and immediately to the right of the visible region or slightly longer wavelength is the IR or infrared region, coming from the proximity to red light. Now let's pause the video and practice. What is the frequency of a laser with a wavelength of 650 nanometer? And what is the color of that laser? So inspecting the table would give you a color of red. If you convert 650 nanometers to meters, you get 6.5 times 10 to the negative 7 meters. To solve for frequency, we would divide the speed of light, c, by 6.5 times 10 to the negative 7 meters to get a frequency of